Okay, so now something I mentioned at the end of class last time was this idea that when we pass a list into a function, so we started writing, I think I started the function for you, right? So insertion sort takes in a list, and I just made a quick modification to that list. I never returned it, so the guy out here wasn't receiving a response. So, I created a list here. I printed out that list, so it showed me all my original numbers. Then I passed that list into my function, but I didn't say a list is equal to whatever this guy returns. I never did that. I just passed the list in and didn't think anything of it from that point forward. And then I just haphazardly printed the list again after whatever this guy may or may not have done to it. And what we saw is that this change did in fact permanently modify the 14 to be a 5, right? Okay. I think we had talked about this when we were talking about, did we talk about pass by value versus pass by reference when we were talking about the weakness of C++?
Yeah, and we talked about graffiti in your garage.
Yeah, right. Okay, good. Spray painting my garage door, that's right. Okay, so, the idea is that in an older language like C++, the programmer is empowered to decide whether they're going to pass something to a function by value or pass something to a function by reference, by address. Okay? In more modern languages, that syntax has largely been removed. And instead, the decision is made for you. I probably said something along the lines of, if you were having a party at your house and it was at 8 p.m. tonight, would you hand me your house? Or would you give me the address where I can find your house? Okay? You would not pass me your house by value. You would not hand me the whole house because it's heavy. Instead, you'd give me a little piece of paper that had the address, or you'd text me the address. The paper was for your benefit. Yeah. Okay. You'd hand me the address, and I would go and find your house in memory, right? Somewhere in the neighborhood. And we can say that in real life, that always makes sense, correct? It would never, ever, ever make sense for you to hand somebody the house. Now, having said that, every now and then when you're writing computer software, reality and programming solutions aren't necessarily identical. Every now and then. But a majority of the time, and certainly at our level right now, we want to, and if you remember back when we first introduced the idea of a programming language, it's a power tool that tries to, we're not meeting it halfway. We're not coming halfway and trying to communicate with this alien computer, right? The programming language comes as far to our side as it can, okay, without speaking English, and says, okay, you tell me what you want to do in a way that's similar to how you already solve problems. And I'll do the heavy lifting of trying to tell the computer how to accomplish that. Okay? So, the job of a programming language is to empower us to solve problems in a way that we already solve them in real life. So what I kind of teach is that, at least as a beginning programmer and even an intermediate programmer, and a majority of the time as an advanced programmer, the way you're going to solve your problems in your software is going to be identical to the way you would solve it in real life. Right? Last couple of classes we've talked about having like a deck of cards and with some numbers in it, and how would you sort through these things? How would you search through these things? Just thinking about that scenario in real life and then trying to write a mimicking solution in software, right? In code. But we can imagine that at some point in the future, we might run into some problem where, because programming can be flexible, we're allowed to break the laws of nature, right? We can actually accomplish something that we really couldn't have done it that way in real life, and that might be better for us. Kind of brings flashbacks to the Matrix where Morpheus fights Neo, and you got the rules of the system, blah blah blah, all that crap. Stop trying to hit me, that stuff. All right. So every now and then we run into a scenario like that in computer programming where we're potentially limited by some of our more modern languages that they don't let us accomplish something that we want to be able to accomplish. Okay? We might, under a very specific circumstance, want to, in the programming world, hand somebody the actual house. Okay? There might be some weird problem somewhere where that may be beneficial. Okay? But in real life, it would never make sense. So for right now, pass everything through the filter of how would you solve this in real life. Okay? And once you know enough about that, then later on, you can be frustrated if a language doesn't quite give you the couple of hooks you might need to accomplish something quirky. Okay? So in a language like Python and a language like Java, the language we'll be using next semester working with Android Studio, those languages make these decisions for us. Okay? They say whenever you have something bigger, okay, a list of stuff, an object, which we're going to be talking about this second 8 weeks here, stuff that's more than just a number or a character or something like that, just to kind of give you the evidence of this. Let me write another little function. We'll just call this guy do something. And we'll take in a variable a, and I'll set a equal to 5 here. Let's just comment these out. Well, so I'll just delete them for right now. Let me keep a list because I don't want to have to type out a list again. We'll sort that guy in a few minutes. But let me go ahead and say b is equal to 7. Then we'll go ahead and we'll print out b. Then I'll call do something, passing it b. B will go in for this variable named a. We're setting a equal to 5 and doing nothing else. We're effectively doing the same thing we did up here, right? The difference is that this animal was a list. This animal was an integer, right? Now I'm going to go ahead and I'm going to print out b again. So b started off as 7. We'd expect this line to print out a 7. Then we're going to go ahead and pass b into do something. It'll come in. A will point to the same place as b, if you will. That's the way we might think of it right now, okay, based on what we learned right here. Then we'll go ahead and set that variable equal to 5. And I'm going to go ahead and print b again here. What do you think is going to output? You think 7 and 5? Do we all agree that this one's going to be 7? Okay, we're good on that one, right? All right. So how many of you think this is going to print out a 5? How many people think it's going to print out a 7? We always have such poor voter turnout. Okay. Okay. Exactly. Well, we didn't quite get half the class. What percent of the population does vote? 60-ish? Now, we had nowhere near 60% of the population in this room vote there. I'm thinking like 25% had hands up. All right, so some of you think this is going to be 7 and 7. Some of you think this is going to be 7 and that this change here will be permanent and we'll see a 5 here, correct? All right, so let's go and look what happens. We have 7 and 7. So it works in the opposite manner to how we saw it work with the list, right? This tells us that when we pass a list in, something bigger like that it is passed by address, okay? We hand them that piece of paper that says, where can you find this dude in memory? So that when we make a change here, that change we're making is actually up in memory where it actually lives. Where in this case, when I handed it that A, I'll just show you here real quick just so you see that A did change. Okay, I'll print out A in there. So now we should see 7, then 5, then 7 again. Okay, because the 5 printed out inside of here. So we'll see that it actually did change locally. There's our 7, 5, 7. Okay, so what's happening here is when we passed the value of B in to this guy, it was passed by value. We gave them a copy of the 7. Say, here's a 7. You store it in your own variable. Any changes that you make are local to whatever you're doing. When we come back to my world here, B is still equal to 7. Does that make sense? So this guy was passed by value. Small things we can think of as a general solution right now. Small things are passed by value. Larger things are passed by address. Okay? That might not be true forever. Okay, but as a general rule of thumb right now, you can kind of think like that. Okay, just like in real life, if you hand somebody, I think I probably used the quarter example in class. If somebody asks you if you have a quarter on you, right? Like any of us carry change, but she has the pen and paper, so maybe she's got change too. Okay, so somebody asks for a quarter, you don't send them on some chase to the last place you saw a quarter, right? Yeah, it's in the gutter outside. Just down the street around the Circle Drive, you'll find a quarter on the. Yeah. You don't do that, right? You either tell them to get lost, or you reach in your pocket, you hand them a quarter, and you relinquish the quarter, right? And if you have 2 quarters in your pocket, you're giving them a copy. And anything they do with that quarter, if they melt it down or something like that, it had no impact on the quarter you still had in your pocket, right? They're separate quarters. You gave them a copy of the quarter. That makes sense? As opposed to me handing you my house and you spray painting the garage door and I'll notice when I get home. Well, actually, no, that's actually the wrong thing. If I hand you the house and you spray paint the garage door and the copy I gave you, I won't notice when I get home. But since houses are big, we always give people the address. So if I give you the address of my house and you run to that place in memory and spray paint the garage, when I get home, I'll notice, right? I might not notice. I don't usually notice things like that. I'll notice when I get inside the house and my wife starts screaming that somebody spray painted the garage. That's when I notice things like that, and it's. Yeah, I spray paint my garage. You should do that sometime. I would find it hilarious. I might be in trouble for a week, but it's like, look, I didn't even think about the consequences of my lecture. That would actually be pretty funny. Okay, so does that make sense, that idea of passed by value versus passed by address? Now, in older languages, as a programmer, we were empowered to make that decision. Okay, and that was kind of the problem with a language like C++, at least as a teaching language for your first language. Once you're an advanced programmer and you understand you understand this concept, then you might even appreciate the fact that you get to choose. Okay, and it won't be that big a deal to put the little extra syntax in there of whether you want something passed by value or passed by address. Okay, instead of just letting the default happen. Python is a newer type language. It makes the decision for us, so we're stuck with that decision. Okay, that's a half truth. That's a 90% truth. For us in here, though, it's 100% truth. Right? So lists, they're bigger. They're passed by reference. Okay, we get a copy. We get the address where it lives. So changes are permanent. We do not have to return the value in order to see the change. As opposed to in here, if I wanted to see that change in A, I would have had to return A. I would have had to say B is equal to, I'm going to overwrite B with whatever value do something on B returns. Now I'm changing the value of B out here with the result of this function. And the result of this function is to change whatever was passed into a 5 and then return it. And then B is actually being modified right here. Okay. Now we'll see 7 and 5 because we returned that value rather than relying on it being modified in memory. Okay, so here's our 7 and our 5. Okay, now, any questions on that pass by value versus pass by reference stuff? Makes good sense? All right, so let's go ahead and get rid of the do something thing. We'll keep our list. Let's go ahead and write insertion sort. All right, so with insertion sort, we drew the pictures last time. We decided that the idea is we're getting a list passed in, and we want to start at position 1 in that list. We had a couple of variables that we needed to have, right? So we kind of have to have our start position, current start position. We need to have maybe a dude called, I usually call him the follower, right? You say it creepy, is the follower. The follower follows. So what the follower does is when something swaps towards the front of the list, the follower does the following to keep track of the the guy as he's voyaging towards the front of the list, because we don't want to forget where we last started from, because we need to start at the next bucket over next time. That makes sense? Okay, so that guy stays constant. So what we're going to start off with here is we're going to take this one little step at a time, and we're going to create a loop that'll go through our list through all of the starting positions. That is position 1 through the last legal position in the list. Okay, so if there's 5 elements in the list, we should go visit 1, 2, 3, and 4. Okay, those are going to be all of our start positions. So I'll say for cur start pos in range of 1 to length of our list. And I'll just go ahead and print out cur start pos, just so we see that guy go through the correct numbers. Okay, he's not doing any sorting yet. But if I gave him a list like this that has 6 elements in it, the places we're going to start from is we're going to start here and bubble this guy towards the front as much as we can. Then we're going to go here, then we're going to go here, then here, then here. So we want to see bucket 1, bucket 2, bucket 3, bucket 4, bucket 5 in a 6 list. All right. So when I call insertion sort right now, I want to see 1 through 5 print out, proving that we've taken cur start pos on the correct voyage. All right, before we do any logic stuff with it. Does that make sense what I'm doing here? All right, so we'll go ahead and call insertion sort. We'll pass it our A list. We'll run this guy, and we will see an error message because I put a colon there instead of a comma. There's our 1 through 5. Okay, so cur start pos is visiting the right places. All right, now we need that variable follower. Okay, and the follower always gets reset to cur start pos each time through our outer loop, right? So each time through we say, okay, well, the follower is going to start at the same starting point, but that's the dude we're going to allow to change as we go back towards the beginning. Okay, so we'll go ahead and introduce our follower in here. So call this guy the follower is equal to cur start pos. Okay, and as of right now, the follower will always be equal to cur start pos. We're not doing anything special. All right, so we have our follower. Now inside of this loop, as we visit each of these guys, what am I doing with this guy? I'm going to ask the question, should this guy move forward in our list? And before I can ask that question, I have to say, do I currently have a place before him I can compare him to? All right, so this guy is currently at position the follower in our list. He's also at position cur start pos because those two guys are synonyms for each other right now, right? But we've said we're going to allow the follower to arbitrarily subtract stuff from it to follow something towards the beginning of the list, knowing that we'll always reset it to the next cur start pos when we come back up to the loop. All right, so what we want to do here on the inside is we want to say, I want to move this guy towards the front of the loop front of the list as far as he can. Then I want to move this guy towards the front of the list as far as he can. How many times does this 3 move? Twice. How many times does this 21 move? 0 times, right? 21 shouldn't go in front of the 14. What about the 74? None. 15, he'll move. So some of them move no time, some of them move multiple times, right? So when you hear that we need to do something potentially multiple times, what kind of structure, in our problem-solving structure, the way human beings solve problems, what kind of thing are we thinking about? Some kind of loop, right? Some kind of loop. And we go back to that idea of remembering stuff, so our memory, asking some questions. We're going to be asking questions here, and then repetition. In this case, we might have to do something multiple times. So we're going to write a while loop here that's going to try to move something towards the front of the list as far as it should go. That make sense? All right, so each time through this for loop, we're going to try to make the current position, so we'll put a little comment in here, try to make val at the follower, move towards the front of the list. That's what we're going to try to accomplish next. So we're going to do that as long as something is true. Okay? What must be true? We must have something we can compare. Okay, we got to have, there has to be somebody before me. That is that the current value of the follower is not 0. Okay? If the current value of the follower is equal to 0, that means we're already at the beginning of the list. I can't compare to the guy before me, or otherwise I'm going to get an error. Because bucket -1 isn't a thing. Make sense? So we're going to say, while the follower is not equal to 0, or you could also say while it's greater than 0, that'll be the same thing in our case here. So while it's greater than 0, and Python 3, it's spelled out and, right? Like that. Most other languages like Java, it'll be ampersand, ampersand. I think it's that way in Python too. But in Python 3, you spell out the word and. So as long as the follower is greater than 0, we know at that point, we know we are allowed to check the guy before us. And the guy before me is less than me. Okay? So the guy at position, the follower -1, is, well, actually, in this case, it'll be greater. The guy at position, the follower -1, is greater than the guy at position, the follower. If we want to ask it the other way around, we could say the guy at position follower is less than the guy at position, the follower -1. That'll have him bubbled forward. Well, he won't do the bubbling yet, but this says we should do the bubbling. So, and our list at bucket, the follower, should come before, and it's LST, not, there we go, should come before LST at bucket, the follower, -1. Oh, did I put a, oh, I'm good. All right, so as long as we're not at the beginning of the list, and the current guy we're looking at should come before the guy right before him. If that's a true statement, we need to do a swap. And then we follow. So we do the swap, and then the follower subtracts, gets decremented, so he follows the guy towards the beginning. We loop back up to this inner while loop, and we ask that same question again. Has the follower reached the beginning of the list yet? If no, do we need to swap again? All right, so for our swap, we're going to need a temporary variable. So we'll say temp is equal to LST at bucket, the follower. Ay, ay, ay. I don't like this keyboard. Then we'll say LST at bucket, the follower is equal to LST at bucket, the follower, -1. And then we'll see LST at bucket, the follower, -1 is equal to temp. That does our swap. So preserve one of the two positions that we're going to be overwriting. Then go ahead and overwrite the position we just preserved. Then overwrite the other position with our preserved value. Make sense? So we could have set temp equal to list at the follower or list at the follower -1. But whichever one we preserved, overwrite that one first. Okay? So this will do our swap. And then we say the follower is equal to the follower -1. The follower follows towards the beginning of the list. That makes sense? So this while loop here will end either naturally once we get to the beginning of the list, or as soon as the current value that we're following should not come before the guy before him. So once he's moved as far forward in the list as he can possibly go. That makes sense? Okay. Now, as a review here, when we use an and, So that's one of our Boolean logical operators. Our programming languages are smart enough to know that in order for an and to be true, both sides need to be true, right? So if we fail this test, it won't even try the second side. And that's an important thing here, because if you look at this code over here, you see that this will cause an error sometimes. If we're at the beginning of the list and we try to access bucket -1 here, it's bad news bears. We're going to get a runtime error. Okay, we don't want it screaming at us in the middle of the program. So we can have comfort knowing that because this is an and, if we notice that we are at the beginning of the list, if the follower is 0, that this part of the code will not even try to execute. Because Python is smart enough to know that, hey, this is an and this was already a false. I'm not going to waste my time doing anything else down there. Because it doesn't matter what happens with it, this whole thing is a false because of the and. Does that make sense? So like if you want to think about this in real life, let's say you're thinking about going to the pizza place for lunch, and you're not sure how much a pizza is, okay? And you look in your wallet and you find out that you have no money, okay? Do you have to go to the pizza place and find out how much of a pizza is if you know you have $0? Okay, so you're not going to waste your time walking to the pizza place to look at their menu or going to Google and checking their menu if you know you couldn't afford any price. Does that make sense? So kind of the same thing's going on here. All right, so this while loop is all happening inside of this for loop. Okay, it's indented under this for loop. So this guy keeps going as long as the current guy we're following should come before the guy that's inside of him. Keeps doing the swap, okay? Or until we finally get to the front of the list and he ends naturally. So at that point, we fall out of the while loop. So I can put a little comment here. So I'm not inside the while loop anymore. So I can say at this point, we have bubbled the follower as far towards beginning of the list as possible, right? That's what we've done for the current version of the follower. Then we spin back up. The follower gets reset to the next version of cur start pause, because cur start pause is now the next number higher, okay? And then we do this whole thing again. We take the new follower and bubble him towards the front as much as we can do. That make sense? All right, so notice we're not returning anything in here, and a lot of the code is comments that I put in here to explain what these things are. Just as a reminder, when you start with a pound symbol, that's a comment, a single line comment, so these are not things that get executed. This is just for human eyes only. Anybody know what the multi-line comment is for Python?
I believe it's 3 single quotes.
3 single quotes?
Yeah, there's no specific multi-line, but that's the best.
Yeah, in C, it's this. It's actually this. So C, Java, all those, it's like that. That's what it's like in all those languages. So you're suggesting it's that and then that?
Quotes, not colons.
Oh. Single quotes or double quotes?
Single.
Does that snap us out of it?
Yeah. And that should just be ignored by the...
Yeah, turn green seems to make some sense. And you said you had tried this? Oh, you just saw it from some, yeah. I mean, that syntax you referenced is almost all of our modern languages are C-based languages, and they all use that because that came from C. So C, C++, Java, C#, they're all like that. Yeah, so you can write multi-line comments if you want. Every now and then I'll do that, but because we're not confident on what that is, I'll just go ahead and throw it like that. Just put a comment in front of each of your individual lines and move on with life. Okay. So this should be insertion sort. We don't have to return anything because any changes we're making to list in here, whenever we do our swaps, that's happening actually up in memory where it lives. Make sense? Okay. So we'll go ahead and we will go ahead and print out a list beforehand. We'll call insertion sort in a list, and then we'll print out a list again. And it should be sorted after we've sent it into the insertion sort function to sort the thing, right? So let's see that happen. So there's our sorted list. All right, that makes sense? All right, so let me... Well, let's leave it there for now. So now that we have a sorted list, last time we talked about a binary search or a dictionary search, right? And we described how this algorithm worked. So we described it in words. Let's look at a picture of this guy now. So this was insertion sort we described in words. I'm going to go ahead and I'm going to steal this guy. Okay, so now I have a sorted list, right? Okay, so this is after insertion sort. So now we're going to look at what is binary search. All right, so this is going to be a more efficient search than we had before. So when we call binary search, we're searching for a specific value. All right, so let's say we're searching for the number 1. Okay, and we want to know whether 1 is in this list or not. Okay, so we're going to search for the value 1. So let's go. We'll have this will probably be the parameter for our binary search function. So let's call this val to search for, and we're searching for a 1. All right. Now remember, with a linear search, which we looked at before, we start at the beginning of the list and just keep trucking. And in this particular case, that actually would have been a smart move, right? Because our value we were searching for was found right away. But we don't necessarily know that because we're writing binary search to be generic. No matter what value you pass me, I'm going to search in list for that value, but I'm going to try to do it in a more efficient way than just linearly walking through all the stuff. Okay. Similarly, when we talked about last time with having a phone book. If you're looking for Zaffiro's Pizza, you don't start on page 1 of the phone book. You know, you kind of zero in on the portion of the book where you kind of know it is. All right. Well, to write this generically, since we have to write the algorithm that can be followed every single time, what we do is we keep dividing our list in half. All right. So we're going to have to figure out where the current middle of our list is. So we'll have another variable here. So middle. And initially, we just eyeball it. Middle is this guy, right? So middle is bucket 2. How did we get bucket 2? Okay, the length of the list divided by 2. Okay, so I'm glad you said that. We're gonna run with that for right now. Let's see, is that gonna work for? We're going to run with that for right now. It's going to seemingly work the first time. So she wants to take the length of the list divided by 2. All right. And right now our focus is on the whole list, correct? All right. So length of the list divided by 2. So we got 4 divided by 2. So that gets us our middle, which is 2. First question we're going to ask. Here's bucket 2. Here's the value at bucket 2. Is it the guy we're looking for? Is a 1 equivalent to a 4? It's not. Okay, not the guy we're looking for. All right, so since it's not the guy we're looking for, we haven't found it yet, but we shouldn't give up. Now we ask the question, if the value we're looking for is found in our sorted set of data, would it come to the left of a 4 or to the right of a 4? The left. So now all we care about, we know it's not this one, right? So we care about everything that came before that in our list. Make sense? Okay, so we kind of need to keep track of where the beginning and ending of our list is. Let's give ourselves a couple other variables here. So initially, begin was 0, end was 4. Okay? So in terms of begin and end, what can we amend our function for middle to be? Can we say end divided by 2? N divided by 2 will give us a 2. Okay? That'll be the equivalent wrong answer to what we had before. So we'll stumble in the right direction. Okay, so n divided by 2. So 4 divided by 2. Now keep in mind, before she said length divided by 2. And the length of this guy is actually 5. 5 divided by 2 is 2 if we use integer division, right? Because not all lists are equal, or are going to be an even number, okay, or an odd number. So we have to be able to, and it's not important that we go to the exact middle. It's only important that we always go to the same calculated position. We use the same calculation for figuring out middle each time. Okay, so for right now, we'll say n divided by 2. So same thing happens. We say, okay, is this what we're looking for? No, it should come to the left of this. Fine. So we need to now amend begin and end. End, begin stays where it used to be, but end becomes 1 less than middle. So end is now 1. Now we recalculate middle. So 1 divided by 2 is 0, right? So 1 divided by 2 is 0. That gets us this place as our middle place. Now the reality is, if we looked at a 2 list like this, either one of these sides could have been our calculated middle, correct? Either one of them could have been. But we always want to calculate it the same way. So our current algorithm says the left-hand side will always be the middle when we have an even number. So middle is 0. We're right here. Is that the guy we're looking for? Yes, it is. We're done. Now, let's back up for a second. Well, we'll keep trucking here. Let's actually say it was a 3. The value we were actually looking for was a 3. All the algorithm we've done up to this point, still the same. The only thing that's changed is now our answer to this, is this the guy we're looking for, is now no. Not the guy we're looking for. Is the guy we're looking for to the left or to the right of this value? To the right of this value. So when we go to the right, we actually make begin 1 greater than middle. So begin is now middle plus 1. So now the beginning and ending of our list is the beginning and ending of our list is the same, which means this is our last check, right? We're last time through our list. We don't even calculate middle in this case. Or could we? Certainly can't do it the way we've been calculating it. The way we've been calculating middle is doing n divided by 2. Well, n divided by 2, 1 divided by 2 is going to give us a 0 again. So now we're going to check this guy and again ignore this guy right here. In terms of begin and end, how could we get a middle that's this while still getting all the other middles the same way we had them before? I initially wanted to get a middle of 2. Then I wanted to get a middle of 0. Now I want to get a middle of 1. How can we modify the way we were calculating middle such that this particular one works? Round up? No, round up would have given us, so 4 divided by 2, In this particular case, that would have worked. What if we took end plus begin divided by 2? 4 plus 0 is 4, divided by 2 gives you 2. 1 plus 0 divided by 2 gives you 0. 1 plus 1 divided by 2 gives you 1. Make sense? So this guy is end plus begin divided by 2. That's the formula for middle. Okay? And we would have seen it doesn't work. We would have broken down earlier if we went on the right-hand side. Okay, so we find our answer at position 1. Our last middle is 1 plus 1 divided by 2, which is 1. Is that the guy we're looking for? It is. Now let's say we were looking for a 7. We start off at our middle. 4 plus 0 divided by 2 is 2. Is a 4 a 7? Nope. Should a 7 come to the right or to the left? Should come to the right. So what do we do? And initially begin was 0, end was 4. We're going to only look at the right-hand side. So we're going to start begin off at middle plus 1. So now begin is 3. 4 plus 3 is 7, divided by 2 is 7 divided by 2 is 3, right? Truncated. So this is integer division, the double slash. Okay, so we're at our bucket 3 for middle. So this guy's currently 3. Is this the guy we're looking for? Nope. Should a 7 come before or after this guy? After. So what do? We set begin to be 1 larger than middle. So begin is now 4. 4 plus 4 is 8 divided by 2 is 4. Here's our middle. Is that the guy we're looking for? It is. What if we were searching for a 9? Everything up to what we're doing right now is the same, right? We got to this point right here, and we're going to say, is that the guy we're looking for? Nope. Should it come to the left or the right of this? If 9 existed, it would come to the right in a sorted list, correct? 9 is bigger than 7. We don't have a right. Okay, we're done. We cannot allow begin to become greater than end. So that is our end point. So as long as begin is less than or equal to end, we keep doing this, find the middle, check the answer. While begin is less than or equal to end. As soon as this is no longer true, we can say it's not found. That make sense? So for your homework assignment, we're going to write a binary search. This guy's going to take a val and a list as a parameter. And this guy should return the position where val is found. And I'm going to say a position where val is found, because this won't necessarily guarantee it's the first position because of how, depending on how you calculate middle. So some position where val is found following binary search, or a -1 if it is not found. That makes sense? So kind of like the index of thing, but you're not necessarily ensuring whether it's the first or the last. You don't even have to worry about that part. Just write binary search and return the middle where it's found. So you'll be returning the position of middle. Or return a -1 if it wasn't there. Make sense? All right, so I'll give you the code we wrote in class today as your starting point, and I will put this up on Blackboard, and I will see everybody on Monday.